Fairness. It's a very misunderstood topic. Most people think they know what fair is. Sometimes they're a little confused, sometimes they're biased. Children seem to have an innate sense of fairness, a very strong one. And there are even studies that suggest that dogs have a built-in sense of fairness. There are dogs that have been studied where they will stop performing a task if they see another dog getting a greater reward for that same task. They know that's unfair. Mathematically, there's a definition of fairness, and it's fairly simple actually. I showed you a video a little while ago on something called expected value. Well, if you're playing a game, you can determine, if it's a game of chance, if it's mathematically fair or not. And the mathematical definition of fairness is that for any activity in the game, every player's actions have the same expected value. Now, we talked about expected value before, but let's review a quick idea of how expected value would work in a game. So we're going to talk real quickly about a very, very simple game. Someone you know is going to propose a coin flip game to you. Very simple coin flip game. Rules will be simple in this example. A coin will be tossed after you pay $1. Coin's going to be tossed after you pay $1. Heads, you get $1.50. Okay, that seems 50 cents. All I got to do is say the word heads. If you get lucky in the air, you make a 50-cent profit. Tails, you get nothing. Now, the way we calculate expected value, which I went over in more detail in the last video, was you multiply the probability of something happening. There's a 1/2 probability that you'll get heads. And in that case, that has an expected value of 50 cents. Why 50 cents? Well, you paid $1 to play this game. And if you win, you get $1.50. That's only a 50-cent profit. The only new value to you is that 50 cents. $1, you already had that. Then we add to that the probability of tails coming up, of losing this game. Now, losing this game isn't free. You paid $1 to play. That's a negative $1 value. So what this expected value is telling you is that half the time, if you play this game over and over again, you should make a 50-cent profit. The other half the time, you should make a $1 loss. We can add these two things together. Half of 50 cents is 25 cents. Half of $1, well, I don't really want a plus sign there, because half of a negative $1 is minus 50 cents. So that's negative 25 cents. Now notice this is not even a possibility. There is no one time where you can play this game and lose a quarter. You'll either be handed $1.50, which is a 50-cent profit because you paid $1 to play the game, or you'll be handed nothing and it'll be a $1 loss. This isn't even a possible outcome of any one game. But if you play this game over and over and over again, you should expect this to be your average outcome. You should average a 25-cent loss per time you play the game. This game's not fair. There's two players. One of them has an advantage. It's not you in this particular case. How would you make this game fair? Well, if we were to make this game fair, we would just have to change one thing. If you win, you would get handed $2. If you were handed $2 per win, well, that would change things a little bit. if you won, your change in your value would be plus $1. If you still paid $1 to play, but you get $2 when you won, nothing when you lost, your expected value would be 1/2 the probability of you winning times $1, your profit, plus 1/2 times negative $1, which is what happens if you get nothing in return for paying your original dollar. Negative $1 is your loss. Probability of if you win plus probability if you lose. This is not going to work out to negative 25 anymore. This is going to work out to 0. And that is the mathematical definition of a fair game. Your expected value is 0. Same is true for the guy you're playing against. Either he goes home with an extra $1, or he hands you $2 after you gave him $1. Half the time he should wind up with nothing. Half the time he should come out ahead, half the time he should lose $1. He's going to have the same expected value. That's a fair game. Same thing happens in both cases. Now, a lot of games appear to be fair, but aren't. That's because a lot of people don't understand the probability behind the games. Let's do a quick review of counting and probability to show another way a game can be fair or unfair. So, I'm going to do an example. I'll tell you in advance, this is an unfair game. Here's an unfair game that may appear to be fair. Do another coin toss game. First, let's pay $1, okay? Make this really seem fair. Pay $1. Toss 3 coins. So you're going to pay $1. You're playing against another person. You're going to pay $1, and then they're going to toss 3 coins. Fair coins, no cheating involved there. Now, when he tosses the 3 coins, here's the rules that determine the outcome. If the coins come up heads, 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 or tails, 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 you win. That's 2 ways you can win. All heads or all tails. Now, if the coins come up, and if you win, you get $2. Guy you're playing, he puts $1 in, you put $1 in, you win, you go home with the pot. You take on both dollars. High stakes game here. Now, what else can happen? Well, if the coins come up 2 heads, 1 tail, or 2 tails and 1 head, you lose, which equals nothing. Which isn't really nothing because you lost the $1 you put in. But that's how the game will be presented to you. Pay $1, you either go home with $2 or nothing. Now this seems fair. This seems very fair on the surface because there are 2 ways for you to win. 3 heads or 3 tails. And there's only 2 ways for your opponent, the other player, to win. You get 2 heads and 1 tails, or 2 tails and 1 heads. And these are the only 4 things that can happen, right? You either get 3 of these and 3 of these, or you get 2 heads, 1 tail, 2 tails, 1 head. There's 4 things that can happen. Half of those things cause you to win, the other half cause your opponent to win. That's fair, right? If I work out the expected value, I'm going to get half the time him winning, half the time you winning. It's going to be fair. Except it's not. Here's why. This can only happen one way. This can only happen one way. These 2 are a little tricky. You see, when determining the probability of an event, you have to look at every way it can happen. You might not think that 2 heads and 1 tails, you might think this can only happen one way, but in reality it can happen multiple ways, and you have to count each of those ways. If you toss 3 coins, well, let's be clear here. And that's not a clear way to write it. Let's be more clear here. This appears fair. Here's why it's not. but actually. When you toss 3 coins, your actual possible outcomes are 3 times you get heads in a row. You can get heads twice and then tails. You can flip heads, then tails, then heads. You can flip tails, then heads twice. You could flip tails twice and then heads, tails, then heads, then tails. And you can flip heads, then tails, or you can flip tails, tails, tails. Now, by the rules of this game, you win when these 2 things happen, and your opponent wins when these 6 things happen, out of a possible 8. These are all the things that can actually happen. And in determining mathematically how many things can happen, heads, heads, tail is a completely different thing than heads, tail, heads. These are different things. They skew the probability. What this means is the probability of a win for you is 2 out of 8, or 1/4. And the probability of a loss for you is 6 out of 8, or 3/4. I think from the probability now you can see that this game's not going to be fair. But to test mathematical fairness, we always test expected value. The expected value of this activity for you, the average that you would expect if you play this game over and over again, is 1/4 the time you would win $2. But wait, you paid $1, right? It's not getting $2. In the grand scheme of things, that only puts you $1 ahead in the world. And 3/4 of the time, you would expect to go home without $1. You'd lose that $1. So this becomes 1/4 minus 3/4. That is -1/2, which in monetary terms means -50 cents. If you play this game over and over and over again, you should expect to average a 50-cent loss over repeated trials. Keep playing the game, you're going to lose an average of 50 cents per time you play. This is not a fair game, but it appears fair. If all you think about is number of times heads and tails appear, you will only see 4 events. But really, there's 8 things that can happen. And the total number of things that can happen is what determines the denominator when you're determining probability. Appears fair, isn't fair. Other games can fall into that category. Give you another example of a game that appears fair that isn't. If a game involves you rolling 2 dice and adding the numbers that you see, this is the actual chart of things that can happen. This chart is everything that can happen. But a lot of people don't think of that. If I describe an activity as, bring that back, as rolling 2 dice and adding up the numbers, most people think that the things that can happen are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I say, let's play a game, give me $1. I'll put $1 down too. We'll roll 2 dice, okay? And let's say if you roll a 12, you win. And if I roll a 7, I win. You might look at this and you might say, okay, that's fair. I mean, let's see. Apparently, you win 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You win 1 out of 11 times. And I win 1 out of 11 times. That seems fair. But this is not fair at all. Because what's really going on is on this table. When you roll 2 dice and add the numbers, these are the outcomes that you've made up by the rules of the game. But mathematically, there's a lot of ways to get to 7. Mathematically, if I roll a 3 and a 4, I get to 7. If I roll a 2 and a 5, I get to 7. In fact, there's 6 ways that I can get a 7. I can get a 7 by rolling a 6 and a 1, a 5 and a 2. A 2 and then a 5 is mathematically different than a 5 than a 2. When you roll 2 dice, there are actually 36 possibilities. And if you play this game of rolling 2 dice, and you say, put in $1, I get $2 if I roll a 12, my opponent gets $2 if he rolls a 7, what you're agreeing to is this expected value. You are agreeing that 1 out of 36 times you will come out $1 ahead. Yeah, there's $2 in the pot, but one of those dollars was yours to begin with, so you only come out $1 ahead. And 6 out of 36 times, you will lose that $1. Now that's 7 out of 36. What happens the rest of the time? Well, I've made a pretty simple game here. I haven't said what happens. I guess you keep rolling, but for any one play of the dice, that's 29 out of 36 times, nothing happens and you get 0. But still, this ends badly for you. This ends badly. How badly? Well, let's check. Let's pull out my favorite calculator. And 1 over 36 times 1 plus 6 over 36 times -1 is, yeah, it's a negative value. It's not much of a negative value. In fact, according to this, if I've written it correctly, I'm not sure what that times 1 is. Oh, that's times 1. That's why it's so low. This should be a plus. I didn't like that. Okay. There we go. Almost negative 14 cents. You should expect to lose. It's actually a little better odds, a little better than I thought. It's not as much of a loss as I expected. But this is telling me that if you play this over and over again, you're going to lose approximately negative 14 cents. You're going to lose negative 14 cents on repeated trials of the game, assuming that my calculator is correct. I didn't bother to put in the 0 as a possibility. So that's one unfair game. Now, I'm making it sound like unfair games are horrible, that they're a way of cheating. They're not always a way of cheating. For example, here's a roulette wheel, excuse me, for a casino game. Now, a lot of times, you could make a simple bet on red or black. If all you bet on is red or black, if that's the bet you make, if that's a simple way to just spin a roulette wheel, get a result, you'll win almost half the time, but not quite half the time. Roulette wheels go up to 36. They've got 18 of each color. You've got 18 red, you've got 18 black, and you've got 2 green. These 2 green are what skew the probabilities against you. If you make a bet, what happens is it's not half the time you'll win on red, half the time you'll win on black. The denominator is all of these possibilities added up. So the probability of winning on red is the 18 red spots divided by the 38 points on the roulette wheel. If you win on black, there's 18 possible ways to win on black out of 38 possibilities. And there's 2 ways to win on green out of 38 possibilities. These probabilities prevent any one bet from being fair. Now, 18 over 38, that's pretty close to 1/2. You'd think you'd win half the time, but that's okay. You set up a roulette wheel in a casino with thousands and thousands of people passing through all day long. You only have to have an expected value of positive pennies if thousands of people roll through to turn a nice profit. And it's expected to be an unfair game. That's the casino's profit margin. They have to win just a little more often than they lose. And if enough people come through, it doesn't even have to be by that much. And that's how they stay in business. So when you're designing your game, it is okay to design an unfair game. I mean, I'd rather you not maliciously try to fool and lie to people in your game and try and trick them into thinking something's fair when it's not, although a lot of carnival games do that. But a game like this is okay. If you want to design a game that is unfair, that's fine. And when we play the game in class, you had better win more often than your classmates for that to be a good, unfair game. Because an unfair game is one that your livelihood depends on. You're a businessman in that case. You're designing a game that will both appear fair, hopefully, keep people playing, keep them engaged. They'll want to keep playing. They'll want a good chance of winning. But in the end, if enough people play, you have to take home a profit. That's how you win. Now, if you're designing a board game for a family to play at home, it shouldn't be unfair. Unfair games in environments like family game time or friends at a game night, well, the first person to figure out how it's unfair tends to have first person who figures out how it's mathematically unfair then has an ethically unfair advantage over the fellow players. And that usually ends in bitter acrimony, ruined friendships, and separate family dinners, and who wants that? So you really don't want an unfair game in like a board game, family game type situation. You have to go to great lengths to make sure that every player has the same expected value if it's going to be a fair game. So your first question in game design, is it fair or unfair? Do you want the family to have a good time sitting in the rec room on a Friday night, if any families still do that? Or even if they're playing the game on their phones in separate locations. You know, if you're playing Scrabble or Words with Friends with people, you still want everyone to have a fair chance of winning, right? So if you're designing a fair game, expected value for every player has to be 0. Nothing wrong with intentionally designing an unfair game, though. Las Vegas has been built on the idea of the enticing, unfair game. The people like to win at those. They feel more satisfaction sometimes when they beat an unfair game. All right, so that should get you started thinking about the mathematics of how you design a game and how you answer your very first question. Is this game fair?